Hello everyone. Today I would like to present you a framework for using topic modeling to analyze design requirements. Here is the layout of the study. I will first introduce the background section, our in-house requirement datasets, data pipeline. The method we use is called latent Dirichlet allocation. Then I will talk about the generated results and the major takeaways. Requirement management can be grouped into requirement elicitation, analysis, specification, and verification. Within requirement analysis, there is a branch concerning confirmation management. During this process, requirement engineers evaluate the changes and make modifications to the system as necessary. Since requirements are often the result of a collaboration among different teams, it can be difficult to identify all the impacts from an initial change across different domains. For this reason, designers should also organize or visualize requirements more efficiently and effectively. Current complex design can lead to human errors if unexpected changes are not dealt with properly. The challenges in design research, even though we have some requirement representation such as requirement hierarchy, networks representation, or matrix-based representations, we still lack of formal models to capture semantic relations and represent requirements. In the modeling side, it is very challenging to collect information from small corpora, short sentences, or highly domain-specific contents. Why topic modeling? Two reasons. Suppose you have a large amount of the text or data in an unstructured format, you need to quickly understand and interpret the hidden themes. Topic modeling does a better job to capture the underlying structure of documents. Second, topic modeling includes realistic assumptions such as each document contains a mixture of topics. Documents are exchangeable and bag of words. Then why RDA? RDA is a generative model. It performs better than PRSI, which has shown inconsistent in assigning probability to previous unseen documents. Secondly, compared to earlier models which assume each document only contains one topic, RDA can learn a hierarchical structure to represent the latent topics. So once we have figured out the general scope of this work, we propose three research questions. To test research question 1, we implement RDA on our requirement data and generate several topics. Based on the interpretation of those topics, we can determine if the requirement can be represented by this approach. To test research question 2, we implemented 3 different methods to determine the ultimate number of topics. For the research number 3, we use a relevance score to adjust the quality of each topic. And finally, one of the potential benefits of this study is that designers could use topics to narrow down the potential requirement change impacts. This slide will focus on our in-house requirement datasets. The dataset we have is unstructured and unlabeled. Unstructured means that the raw text document contains numbers and symbols. Often a pre-processing step is required to improve the quality of the simulation. And unlabeled means we didn't assign any labels to each sentence. The industrial project we have are acquired from previous research project. Each of them have a various number of sentences and the sentence length. Tokens are the total number of words in the project, and the vocabularies are the number of unique words in each project. Since each project share and use many repetitive words, that's why you can see a huge reduction from the number of tokens to the vocabularies. We also feed the kernel density function and plot the estimated PDF over the data. The likelihood of sentence length is around 11 projects for project 1. Another way to look at requirement documents is to see them as functional and non-functional requirements. Non-functional requirements contains to the themes such as product warranty, instruction, and delivery. And also, non-functional requirements tends to have many low-frequency words. Based on the percentage of non-functional requirements, we can sort project in this order. We pick project 1 to elaborate on since it contains good amount of both functional and non-functional requirements. All three projects will go through the same data pipeline. In pre-processing step, because of the bag-of word assumptions, all the documents can be randomly shuffled, and all the stop words has been removed. The rest of words can be lowercase, tokenized, and lemmatized. Please note that lemmatization may increase the difficulty to interpret the original text data. And then all the terms will go through Rba algorithm solved by Gibbs sampling method. The generative models will be evaluated by both perplexity and the coherence score. And the final result will be visualized by RDA visualization and the word cloud. This slide will talk about RDA algorithm. RDA contains mainly three assumptions. Bag-of word means not only the order of words in a document is random, and also the order of documents in a corpus can be also ignored. In this study, we consider each requirement sentence is a document. Each document contains a mixture of topics, and the entire project is a corpus. Exchangeable just means a conditional, independent, and identical distributed. So with those three assumptions, we can divide the requirement documents into both training and holdout sets. Here we implement a supervised version of RDA. Both alpha and beta are directly prior. We have treated them as hyperparameters. And W is represents the words. So after training process, we generate both theta and phi for further analysis. And perplexity measures how well probability distribution to predict a new sample. And it has been often used in training set to indicate the model convergence, and also in holdout sets to determine the ultimate number of topics. Literature shows perplexity does not always correlate well with humans' judgment, and that's why we incorporate coherence score to also indicate the ultimate number of topics. Finally, after fine-tune, the best perplexity value is acquired when alpha equal to 0.01 and beta equal to 0.1. Since determining the ultimate number of topics is an open-ended question in topic modeling, we have incorporated three different approaches to estimate a reasonable number of topics. The first two are based on perplexity values. The third one is coherence. Here are some results. The L method is defined as feeding two lines to the perplexity values, and the intercepts indicates the ultimate number values, which is equal to 10 in this case. And the second method is alpha equal to 10 over k. K is the number of topics. Here we took 10 samples, and 20 is the lowest perplexity value, which is the ultimate number of topics. And last one, coherence score. As a general rule of thumb, coherence value can be classified into several categories. And instead of taking the highest value, we consider a range of scores from 8 to 16. And finally, we consider a union of those topics ranging from 8 to 20. And after manual examination, another design decision has been made to select 15 topics as the final result. In order to accurately represent requirement documents using topics, three measurements can be considered to determine which term should be included for each topic. Distinctiveness is the KR divergence. It's a measurement of how one probability distribution is different from a second. Based on distinctiveness, a silency score incorporates each word's probability into the equation. Third one is the relevance score. It introduces the lambda value as a weight parameter to determine the rank of words. Here is one mini example to demonstrate its effectiveness. The green bar is the term overall frequency or the saliency score. The red bar represents the estimate term frequency or the relevance score. By changing the default value of lambda from 1 to 0.8, we can get more meaningful interpretations for each topic. In this case, pipe stop is a device to hold the pipes, and those pipes will be lifted from the pipe stops. In results section, we first plot RDA visualization. On the left-hand side, we have topic distributions. Since most of the non-functional requirements have relatively low frequency words, and they are located closer to each other in this 2D subspace on the left. And most of the functional requirements can be found in topics such as 1, 3, 4, 6. And the size of each circle represents the marginal distribution. On the right-hand side, we have word distribution for each topic. Here we pick top 30 words within each topic, and since each term can contribute to multiple topics, certainly not all of the terms should be considered during the topic interpretation. And then we made a comparison study by lowering the number of topics from 15 to 10. And we found both of functional and non-functional requirements has been combined. Most of the functional requirements can be found in topic 1, 3, and the rest of them are contains most of the non-functional requirements. And we found the lower the number of topics can better interpret the non-functional requirements, and the higher number of topics can definitely better distinguish the functional requirements. So therefore, there's a trade-off in decision making. Another way to visualize word distribution for each topic is use a word cloud. The size of each word indicates how much weight every term could contribute to that topic. Having manually assigned labels to each topic, we found that some of the topics can capture particular attributes within a requirement document. For example, topic number 9 describes the units and the dimensions. 3 and 6 captures a particular motion of the pipe, and 1 and 4 are mainly describe the different working stations. And when we cross-compare the different number of topics, we found several topics can be merged together. Like, for example, in this case, both lift and the transfer motion of the pipes has been combined within topic 1. Similarly, project 2 describes a cradle machine design. It mainly talks about supplier's rule or duty, cradle frame layout, or different type of drawing documents or data. Project 3 involves the manufacture of bypass flap, which contains many electronic cabinets and enclosures. And that's why you will see a lot of topics such as indicator lights, human-machine interface, or PLM programming. Here is my final slide. We argue requirement documents can and should be used to organize design documents into topics. This is a supervised process where designers determine the ultimate number and the quality of topics for each design. Lastly, this framework presents a conceptual analysis to help designers to better understand requirement documents and prepare for re-engineering decision making.